Welcome to CSAI Think Tinker Learn. This is part of the new System Design Essential series. The goal here is to give you a solid mental model of complex architectural topics without getting bogged down in the weeds. We're breaking down sharding strategies and hotspot mitigation today. This is a concept first introduction to help you build your system design foundation quickly. If you want to see a deep dive on specific implementation details or a different case study, let us know in the comments. For those who prefer reading, do check out the article, the link is in the description. Now, let's get started. Every scale story starts with a single node, but eventually you hit the monolith four walls. Vertical scaling, just buying a bigger box, reaches an economic and physical ceiling. You'll hit a disk capacity limits, CPU read bottlenecks, where concurrent queries overwhelm I/O and lock contention on write. Plus, fiber optic physics means distance equal latency. To scale, we must move from vertical to horizontal. We distribute the load, but the trick is making sure we also balance it. The core mechanism of horizontal scaling is sharding. We introduce a shard router that inspects the shard key of an incoming query. It calculates the destination mathematically and forwards the payload to specific shards. What's the catch? You need a meticulously chosen shard key. A poor choice turns one shard into a glowing red hotspot, while the others sit idle. You have distributed the data, but you have failed to distribute the work. There are three primary routing strategies. Range-based is excellent for time series or sequential lookups, but very risky for temporal hotspots. Hash-based is the king of even distribution for uniform data, though resharding is costly. Directly based gives you the most granular control, allowing you to isolate whale tenants on their own hardware, but it requires maintaining a manual lookup table. Your choice depends entirely on your specific data access patterns. The breakthrough for distributed system is consistent hashing. By mapping both nodes and keys onto a 2 raised to the power 32 ring, we minimize the data movement. Without this, adding a single shard would require a catastrophic 99% data migration across the entire cluster. This is the logic that powers the world's most scalable databases. To fix a problem, you must first diagnose it. There are three types of hotspots. Number one is temporal, sequential time step crashing into the newest node. Number two is popularity. Driven by Zipf's law, there is a viral celebrity record receiving a massive block of reads. Number three is structural, a biased shard key, like sharding by country code, where one country is permanently oversized. You cannot mitigate a hotspot until you know why it exists. Mitigation number one is virtual nodes, or VNodes. Instead of one position on the ring, we assign each physical node 100 to 200 phantom positions. This averages out the hash distribution. It ensures no physical node owns a disproportionately large arc of the ring. It makes the cluster more resilient and balanced, though it does add a bit of a complexity to the router's lookup table. For write-heavy temporal hotspot, we use key sorting. We append a random suffix like _0 to _7 to a highly active sequential key. This forcefully scatters a massive write spike across the entire cluster. The trade-off is the fan-out penalty. To read that data back, the system must query all sorted versions and merge them in memory. It's a powerful tool, but use it surgically. When dealing with read popularity, we use whale shards and cache firewalls. We isolate the top 1% of heavily accessed keys to explicitly over-provision hardware. More importantly, we place a distributed cache like Redis in front. This firewall absorbs 99.9% of spikes before they ever touch the database. Just watch out for the cache stampede. Mitigate that probabilistic early expired techniques like xfetch. To scale read throughput independently, we use read replicas. We clone the data. The primary node handles all ACID writes, while the router distributes read across multiple read-only copies. The danger here is replication lag. If the replicas fall behind, users see stale data. If you need strict read your writes consistency, you must route those specific users back to the primary node temporarily. The blueprint for a perfect shard key rests on four pillars. High cardinality. Don't shard by booleans. Uniform distribution. UUIDs over sequential integers. Stability. Don't shard by values that update, like email. And query locality, like minimize cross shard scatter gather. If your shard key doesn't hit all four, your cluster will eventually lean. Advanced patterns often require a composite key. We split the key into two parts. The partition key determines which physical node the data lives on to satisfy locality. The clustering key determines the sort order physically on the disk within that shard. This allows you to isolate queries to a single node while still maintaining highly efficient sorted retrieval. Let's look at a real world case study. Discord message storage. They originally sharded by channel ID in MongoDB. It provided perfect locality, but popular public channel became brutal hotspots. The fix was moving to Cassandra with a composite key of channel ID and message ID, combined with consistent hashing. This solved both the locality and the load distribution problem simultaneously. As an architect, your dashboard should have three main gauges. Shard size ratio. If the max to average ratio is over 2x, you have structural skew. Number two is P95 latency. If one shard is 10 times slower than its peers, it's a hotspot. Third is replication lag. If it's over 500 milliseconds, your primary is overwhelmed. Monitoring is non-negotiable because a cold key today can go viral tomorrow. To wrap up, sharding is a negotiation. Query performance wants data to be co-located. Load balance wants it to be distributed. Cross-shard transactions should be minimized via smart key design. Capacity should be added via consistent hashing. And node failures must be handled by graceful rerouting. Now, for the community question. Have you ever designed a sharding scheme that worked for 99% of your data but got absolutely wrecked by a single celebrity record or a viral event? How did you fix it? Was it salting, caching, or something more exotic? Let us know in the comments. If you enjoyed this episode, please like, share, and subscribe to CSAI Think Tinker Learn. See you in the next